Hi, Dr. P here, and in this lecture video we'll take a look at the atomic spectrum of hydrogen and the Bohr model of the atom. So let's look at atomic spectra, and we'll get to do a lab about this a little bit later on. So essentially, a gas sample is given a spark and without any oxygen present. And I should note that that's high energy spark. And so the molecules or atoms, because you can do this with a gas like helium, absorb energy, and we have some hydrogen-hydrogen bonds are broken. The resulting atoms are excited. Excited, the T, excited. That is, they contain excess energy. And then the atoms release the energy as light. And the light is released at different wavelengths. And that is the emission spectrum in this case the emission spectrum of hydrogen. Now if we look at a continuous spectrum, so if we shine white light from a flashlight or sunlight through a prism, we get a rainbow, a full spectrum of all wavelengths. However, so we'll say here white light through prism, all wavelengths. But the H2 spectrum, so when we shine the light emitted by an H2 lamp, which is what we would call this, we could also have a helium lamp, a mercury lamp, etc. There may be some street lights out there that are still mercury vapor lamps, and they work this way. We would see that only certain wavelengths are observed, sorry. We also call them lines because, if we had a spectrum here, and, it went from, we had our purple, and then our blue, and then we had our green, and then yellow, orange. I know I'm skipping yellow. I don't have a yellow pen. You'll have to excuse me. And red here. We have that nice spectrum. But for the hydrogen spectrum, we only get certain lines. So, for example, we'll have a line at 410, and then a line at 434, a line at 486, and then a line at 656 nanometers. These aren't exactly the right colors, but you'll see what the actual colors are when we do this lab in a couple weeks. So this means that only certain energies are allowed for the electrons in a hydrogen atom. Thus, electron energy is quantized. So we could draw an energy diagram here where we have our lowest level here. This is our ground state. Let me shift that up a little so you guys can see that. That's our ground state. And then we have higher energy levels. And so we could have, let's say, light emitted, so delta E1 equals hc over lambda 1. And we could have this emitted at different wavelengths depending on delta E2 equals hc over lambda 2. And so the larger the gap here, the higher the energy level of the electron, the higher the energy of light that is emitted. And so delta E here, of course, equals h nu, which equals hc over lambda. Now, the reason why we convert it to wavelengths is that it's kind of a little bit more convenient, I would say, to talk about wavelengths of light than frequency in the visible region. All right. So this is very interesting, and we need to account for this. So how are we going to account for this? Well, that's where Niels Bohr comes into the picture, I should say, and we get the Bohr model of the atom. All right. Now, in the Bohr model of the atom, he proposed that electrons move around the nucleus only in certain allowed circular orbits. So electrons move around nucleus only in certain allowed orbits. Now, according to classical mechanics, a charged particle under acceleration, and a particle that is moving in circular motion, so when in an orbit around an atom, for example, that is constantly under acceleration because the direction of travel is changing. So, by classical mechanics, a charged particle under acceleration radiates energy. So the orbiting electron should continuously release energy, continuously radiate energy, losing it, and then spiral into the nucleus, and boom. Clearly, this doesn't happen. So Bohr assumed that the electron orbital angular momentum, that is the size of the orbits, was quantized. And why this was unclear at the time. We'll come back to that in a later lecture. So the spectral lines are going to correspond to transitions of the electrons from one orbit to another. And he came up with the following equation. The energy of an electron in an orbit is equal to minus 2.178 times 10 to the minus 18 joules times the nuclear charge squared So for hydrogen, it would be 1 squared. For helium, it would be 2 squared, or 4. And that's divided by n squared, where n is an integer, etc. And n equals 1 is the lowest, n equals 1 is the ground state. That is the lowest energy state. So for a n equals 6 to n equals 1 transition, n equals 1 transition, we have delta E equals, oops, not delta, we have E1 minus E6 because it's final minus initial. And if we plug in the numbers and calculate it, it's minus 2.178 times 10 to the minus 18 joules minus negative 6.050 times 10 to the minus 20 joules. And that then equals minus 2.117 times 10 to the minus 18 joules. So notice it's negative, which means that energy is given off. And then we can calculate the wavelength of the light emitted. So this is delta E, because remember delta E equals hc over lambda, or lambda equals hc over delta E. So in this case, lambda equals 9.383 times 10 to the minus 8 meters, or 93.83 nanometers. In UV visible light, often we report the wavelengths of light in nanometers. So this is in the far UV range. UV is below 400 nanometers, less than 400 nanometers wavelength, so between 1 and 400 nanometers, let's say. Okay. Now, there are some important points to the Bohr model. It correctly fits the quantized energy levels of the hydrogen atom and postulates only certain allowed circular orbits for the electrons. We've talked about that. As the electrons become more tightly bound, their energy becomes more negative relative to zero energy reference state, A0 energy reference state, which is where the electron is an infinite distance from the nucleus. That means as electrons are brought closer to the nucleus, energy is released from the system. And that makes sense because that means that electrons closer to the nucleus are lower in energy, which is a favorable state. We'll see when we talk about thermodynamics later on that things tend to go to their lowest energy state. And so if it required energy to bring an electron close to a nucleus, we would never get atoms. And so what he then came up with was the following. If you want to look at it in the form of an equation, we have delta E equals minus 2.178 times 10 to the minus 18 joules times 1 over n final squared minus 1 over n initial squared. So we could use that to calculate our change of energy in any particular atom. This also gives us what's called the Rydberg equation, which is that 1 over lambda equals some constant called the Rydberg constant, RH, the Rydberg constant, equals 1.097 times 10 to the 7th meters to the minus 1 times 1 over n final squared minus 1 over n initial squared. So I'll just say here, or use the Rydberg equation. So the Rydberg equation is helpful in that you can get 1 over wavelength and just take the reciprocal of that to get your wavelength, instead of calculating energy and then doing lambda equals hc over delta E, doing that additional calculation. That's incorporated. The h and the c are incorporated into this constant are incorporated into the Rydberg constant there. Now there's a major problem with the Bohr model. It doesn't work for atoms other than hydrogen. And it turns out it's fundamentally flawed. Electrons do not orbit the nucleus like planets orbiting the sun. But we'll see later they actually exist in stable areas around the nucleus that are known as orbitals. And in the next lecture, we'll look at quantum mechanics, which explains some of the things that the Bohr model doesn't. In the meantime, get familiar with what the Bohr model is and what it's good at explaining and what it's not so good at explaining. I may ask you to, compare and contrast that to the quantum mechanical model later on, or the plum pudding model for that matter, thinking back to chapter 2, I believe. All right. Well, until next time, stay safe out there. Bye now.